This is the board game problem. You are playing a board game. I don't know why you're talking right now. You're playing a board game with a group of friends. At the start of the game, different players are assigned control of certain spaces on the board. Each player rolls 2 standard number cubes, that's dice, and uses the sum of the numbers rolled as the total number of spaces to move their game piece around the board. If a player's game piece lands on a space controlled by another player, the player needs to pay a toll from their collection of tokens. So kind of like Monopoly, you know, you got to pay if you land on someone else's spot. If a player does not have enough tokens to play the toll, they lose the game. Excuse me?
What? I'll stop there.
Why?
Because that's something.
Okay, great. You can go sit over there.
Where?
Right over there.
But then I won't be able to see the smartboard.
Thank you.
Oh my gosh, no.
Okay.
Farewell, guys.
Farewell. They lose the game. So if you land on the spot that someone else is occupied, you lose. Okay? You are currently 5 spaces away from a space controlled by another player. You can assume that that's like either way you go. I don't know that it specifies that you can only move one direction, but just imagine that you're penned in. Either way you go, it's 5 spaces. The toll for landing on that space is more tokens than you have available. Any of the other spaces you could move to with your next roll would be safe. Design and perform an experiment that you can use to determine the probability that you will roll a 5 on your next turn and lose the game. So it's not like you're just rolling one dice, right? And it's just 1 out of 6. You got 2 dice. So you're going to do experimental probability. Okay, you're going to actually do an experiment. So in the space down here below the picture, that's your space for designing your experiment and performing your experiment. So I'm going to hand out your dice. Okay, so this is what a bunch of you told me. I didn't get everybody, but I got a lot of you. Stop rolling the dice. Okay. Okay, let's say that let's say that I only did one of these experiments. Let's say that I'm this blue person at the end. Okay, how many trials did I do?
40.
Well, let's add it up. 1 and 3 is 4, and 5 is 9, and 4 is 13, and 20. So to here was 20, so I don't forget. And then 29, 40.
Yeah, 50.
42, 47. It looks like 51. Am I crazy or is it 51? Okay, it's fine. So, out of 51 trials, okay, what is, excuse me? What do you, okay. So, out of 51 trials, how many times did they get a 4? How many times did they get a 5?
4.
They got 4 5s. Okay? So what is the experimental probability that they get a 5 and lose? So we want this expressed as a decimal. So everybody do 4 divided by 51 and tell me what it is as a decimal.
2.
0.07. 0.0.
We're going to do 3 decimal places because that's what the pre-AP people all do all the time. Yep, 0.078. Okay. So approximately 0.078? Okay, let's say that I'm not this person. Let's say that I am this person. Oh, that's the same. Let's say this person. Okay, so can you guys help me add up this? So I have 0, 1, and 1, that's 2, and 7 is 9, and 7 is 16, and 13 is 29?
Yeah.
and 5 is, right? Okay, so these two 5s make a 10, so that's 39. Another 5 is 44. And then that one's actually 50, right? Okay, so this one's out of 50. How many times did they get a 5?
7.
Okay, so what is the experimental probability for this person's experiment?
14%.
Is it really?
Yes.
So 0.14. What was the number after the? Okay, it is. Okay, it's exact. Yeah. Okay. So, in a small experiment with a limited number of trials, we have a certain amount of variability in our experimental probability, right? For how many 5s, what is the probability that we roll a 5 and lose the game? Okay, so now I'm going to need your guys' help with adding across the columns because we're going to get totals. Okay, who wants to add the 2s?
I do.
Thank you. The 3s? Who's adding the 3s for me? Don't all volunteer at once.
You want us to just add these numbers together, or add them by 10?
Add up these.
Yeah, I know.
Add up the rows, but don't add those.
Oh, okay.
Okay. How many did you get for 12?
I don't think so. I think 2.
Okay, how many 2s? How many 2s?
20.
Okay, how many 3s?
27.
4s? So I need the total number of trials for everybody. Combined trials.
This is actually pretty normal distribution. That's pretty normal. So this is pretty normal.
538.
Gee, I thought you were supposed to stay out in the hall.
But I got my thing done, so now I don't have to roll the dice.
Okay, great. Okay, so how many totals did we get?
I've got 538.
538?
That's wrong. I got 5.
I'm a low gamer, I drink it.
Yeah, I got 540.
Okay, someone got 540?
No, I was
Okay.
530.
Okay, so how many times together did we roll a 5?
20.
Bro,
Nope. 54.
54, I said it.
you said 4.
Okay, so now we just need to figure out our combined experimental probability. What do we get? 54 divided by 538. It's going to be about 10%.
9.8.
We're going to say 0.100.
100%.
Okay, now notice that together we were somewhere in between these more extreme ones. So what do you notice about this? What is the most frequent combination? 7. And then what happens as we go toward the ends?
Decrease.
Okay.
Oh.
Is anyone shocked that it's more likely that we get the middle ones? Okay. All right, flip it. Here we go. We got to move on. All right. Please be quiet. Okay, here we have the sums of 2 number cubes over 10,000 trials. How is the shape of the graph above familiar? Okay, it's roughly symmetric. What does it also kind of remind us of? We got another word. It starts with an N.
Normal.
It kind of looks like it might be normal. We don't know if it's normal. Okay, does it make sense to you that the graph has this shape? Okay, explain why. Like, how many ways are there to get a 12?
Not many.
Okay, how many ways are there to get a 2? Okay, how many ways can we get a 7? Okay, so like a 1 and a 2 and a 3 and a. So is this making sense?
4 and a 3.
Okay, so put it into your own words.
It shows a normal distribution.
Okay, what do you wonder about the graph?
Why is it so symmetric?
Okay, write it down.
Like me and like, she's pretty much said the